Welcome to Unit 2, Lesson 7. And here we're going to talk more about the applications of quadratic relations, and specifically the fact that they have maximum and minimum values. So this is something that's a really important fact about quadratic relations and what makes them different in a lot of ways from linear relations. So in grade 9, when you first learned about linear relationships and you saw how they create a straight line on a graph, you would have noticed that those straight lines did not have any maximum y value or any minimum y value. They kept going in both directions forever and ever. But with parabolas, with quadratic relations, we know that they do have either a highest point, a max, or a lowest point, a minimum. And that means any real-world situations that follow a quadratic relationship have some special value that represents a highest or a lowest value, which might be really useful to us in that real-world situation. So first off in this lesson, we're just going to look at some quadratic relations in standard form and think about how we would find their max and min values, and then we'll see how we can apply this to some real-world situations. Well, if we want to find the max or min value of each of these, we need to find their vertex. And, well, if you remember from our previous lesson, we know that's not so easy to do from standard form. So first what we have to do with each of these when they're in standard form is to convert them to their vertex form using the completing the square method. So this first one I'm going to go through with you. For the other ones, I'm just going to kind of get you started and let you try the completing the square yourself, but it's worthwhile to review it briefly here. So we would say y equals, and then we start by common factoring out the a value from just the first two terms. That leaves an x squared from the first term, and then we have to be careful. What we need to do is take 1.2 and divide it by this common factor that we've pulled out. Divide it by 0.3. When you do that, you actually get a nice whole number. It's 4. And then we still have this plus 4.5 on the end. And then we take this value of positive 4 and to find our magic number, we divide it by 2 and square it, which means we actually get a magic number of 4 as well. And we make sure that we take that magic number and add it and subtract it within the same bracket. Then we take these first three pieces and show how they can be factored. Specifically, x plus 2 squared is how those first three pieces would factor, and then we still have a minus 4. And then, when this minus 4 gets moved outside of the bracket, it needs to be multiplied by 0.3. Doesn't need to be square anymore. So negative 4 times 0.3 is negative 1.2. We're going to then also add that with 4.5. So overall, we have 0.3 x plus 2 all squared and then plus 3.3 hanging off the end. So that is our vertex form now, and that means we can quite literally state our vertex, so that's important. The vertex is going to be at negative 2 and positive 3.3. So when this question asks us what is the maximum value, and it also asks us when it occurs, in this case it's actually a minimum value, we should say. So we can say, therefore, the min value is, and it's the y-coordinate of the vertex, 3.3, and it occurs when x is equal to negative 2. Let's try another one. So now for this one, we're going to do the same thing, only in this case, it'll be stating a maximum value. But again, it's just completing the square. I'll maybe just do the first step for you, just to hammer home something that's really important. So I'm factoring out a negative 3 from those first two terms, so that leaves w squared from my first term, and then I have to take the 5w and divide it by -3. So I can actually just call it -5/3 w. And then I still have -1. And now it's this value, -5/3, that becomes the number that helps me find my magic number. I need to cut that in half and then square it, and then add and subtract and continue my process from there. I'm going to leave that to you to try. So pause it at this stage, restart it in just a moment, and then I'll show you my completed version of completing the square, and we'll talk about what it means. So here's what I got from mine. We can see a couple tricky things that happened. So in order to find our magic number, we had to divide -5/3 by 2, so that'd be -5/6. And that happens to be the thing that ends up in our final factored form. But to find our magic number, we also had to square that. So the thing we added and subtracted was actually 25/36. And then when we moved this one outside of the bracket, we had to multiply it by, well, -3, which is what made it positive. But then when we did the multiplying by 3 part, the way I handled that was, as you can see here, I reduced the 3 with the 36 on the bottom. So I really had 25/12. And then I needed to subtract that with 1, so I turned the 1 into 12/12. And I end up with this final completed form in vertex form. So what does that mean? It means my vertex then is 5/6, positive 5/6, and 13/12. And just keep in mind that these are not just variables representing x and y anymore. They have new meanings. So instead of x, this is really our w value, and instead of y, this is really our a value. So this might be, for example, an equation that relates the width of something, a width of a rectangular shape maybe, to the area of that rectangular shape. And that's what those variables would represent in that case. So we can say, therefore, well, in this case, it's actually a maximum value because the whole thing would point down if we were to graph it. So the max value, remember, and that's a y value, that max value is the number 12/13. So you can think of that like a value for A, or area, and it occurs when W is equal to 5/6. So now let's see how we can apply this exact same procedure to something that connects to a real-world problem. So we've already seen that these quadratic parabola relationships connect very strongly to things that are launched in the air and follow a certain parabola shape as they launch through the air. And if you've ever seen something launched, you know it has a certain maximum height that it reaches, which is really like the maximum or vertex point on that parabola shape that it follows. So here, we've got an equation that represents the height in meters and time in seconds for a rocket that's being fired. And we want to find the maximum height it occurs and when, or in other words, what time that occurs at. So once again, I want you to take a minute, take that equation that you're given there, or the relation that you're given there, and put it into its vertex form by completing the square. Pause the video now and restart it in a moment to see how I did mine. So here's how mine worked out. As you can see, when we common factored out the -1/4, it changed this second term inside the bracket to -12. When we cut that in half and square it, we find 36 is what we needed to add and subtract. That allowed us to take these three terms and factor them into this. And then in the end, we needed to take this 36, move it outside the bracket, multiply it by -4, it became, or -1/4, sorry, it became +9, and then we added it with the 45, and we get this final form that you see. So once again, the vertex form is not really what we were looking for. We're trying to answer questions about maximum values here. So we need to now take what we see and state its vertex. Well, its vertex is positive 6 and positive 54. And then we need to step back and remind ourselves, what does that actually mean? Well, the x variables now are really like t variables or time variables. And the y variable is really like an h or a height variable. So to be more specific, we can say, therefore, the max height is 54. And remember, that was being measured in meters. So is 54 meters, which occurs after 6 seconds. Because time was being measured in seconds. So again, that's the power of vertex form, is it allows us to find a vertex, which means it allows us to easily find, in this case, a maximum value. And in previous cases, it easily allowed us to find a minimum value as well, depending on which way our parabola shape or our relation actually goes. Let's try a seemingly different, but in a lot of ways very similar situation. So now we've got nothing related to anything being launched or anything like that, but we have something else that follows a quadratic relationship. So the concentration of bacteria in a pool is going to be measured t days. So t is really a length of time, but it's measured in days, and that's going to be sort of like our x variable. And c is representing the concentration of the bacteria per centimeter cubed. So in other words, it's sort of like a number of bacteria in each cubic centimeter. We want to find the lowest concentration. So that word lowest is a fancy word of saying minimum value of concentration. The lowest concentration would occur at its minimum value. But also note that we want the day which it occurs. So we're trying to find the t value when that minimum occurs. So it's really like we're solving the same situation that we were in our previous one. It's just that it happens to apply to a completely different real-world situation. So once again, now I want you to take this new equation that we have, or this new relation that we have that connects concentration and time, try and put it into vertex form by completing the square, pause the video at this stage, and restart it to see how mine went. So here's what I got for mine. Once again, the common factoring step created this minus 8t inside of the bracket. When I cut that number in half and then square it, we get 16. So I added 16 and subtracted 16. These first three terms from that bracket then factor into t minus 4 squared. And we move the 16 out and multiply it by 30, and it became negative 480. Combine those last couple terms, and we end up with this final vertex form. Vertex, then, is 4, positive 4, and positive 20. Then we step back once again and remind ourselves, what does that mean in our specific situation? Well, the 4, or the x variables, are really t for time in days. That's how many days have gone by. So 4 days have gone by, and c is taking the place of our y variable now for concentration. So the concentration level is 20. So remember, our goal was to find a minimum concentration. So this vertex point is telling us the minimum concentration must be 20, and it occurs after 4 days. So therefore, the lowest concentration is 20 bacteria per cubic centimeter, which occurs after 4 days. That's what we've found. So we've now seen how useful this ability to complete the square for any quadratic relation is, because it gets it into a vertex form, and that vertex tells us the maximum or the minimum value. A lot of times, though, we may not actually know off the bat what the relation is and what sorts of values go into that relation, so we might have to build that relation ourselves using information from the question. That's what we're going to do here in question 4. So it seems like a much more general type of question. So we're going to have to sort of build everything up ourselves. So we're going to find two positive quantities whose sum is 18 if the sum of their squares is a minimum. So you might have done something like this and remember it a bit from grade 10, depending on how far you got with things in grade 10. But if you haven't, let's just sort of go through how we could tackle this. Well, we need to find two positive quantities whose sum is 18. Well, in general, that means we're looking for two positive numbers for two different quantities. So I'm going to use that as sort of my first let statement, or my first variables that I'm going to define. And I'm just going to use A and B. So let A and B represent the two positive quantities. And then the thing I'm actually trying to minimize needs to have a variable as well. So the sum of squares needs to be a minimum. So I need to create some sort of equation that represents this thing called the sum of squares. And then I need to take that equation and find the minimum value of it, or take that relation and find the minimum value of it, I should say. So the sum of squares, we can just give it a name, s. We're going to give it the variable name s. So in other words, s will represent what the sum of squares is equal to. And we'll talk and remind you in just a moment what we mean by sum of squares. So let's build some relationships or some equations that connect these variables together. Well, how do A and B connect together? Well, there is an important piece of information in the question. It says they sum up to 18. They add to 18, in other words. So here is a simple equation that we can write to connect them. We can say A plus B is equal to 18. And because that's the first little equation that we came up with, I'm going to call it equation 1. But now we need to have something that involves this thing that we're trying to minimize, the sum of squares. So what is s actually equal to? Well, sum of squares means squaring two numbers and adding them together. So the sum of squares for A and B would be A squared plus B squared. And that's what I'm going to call equation 2. So what I'm recognizing now is that I have this relation here that seems like it's going to be quadratic, because I can definitely see that there's some squares involved. But it's a little bit weird, because this side of the equation, well, s for the sum of squares, that can sort of be like a y variable would be in the typical quadratic relations that you're used to. So we would put the y on the left side, and then we have some quadratic relation for x normally on the right side. But on our right side, we have a quadratic that has two different variables in it. So the problem is we have these two different variables, a and b. So what we're going to do is make use of the information from this first equation to try and replace one of these two variables in the second equation. So here's the idea. I'm going to take these and put them together. And in order to do that, I'm going to have to do some rearranging first. So I'm going to rearrange equation 1 and sub it into 2. So in order to do that, I could say, for example, that b is just equal to 18 minus a. In other words, anywhere I see a b, I can replace it with 18 minus a. So s then Normally I would say it's a squared plus b squared, but now I can say it's a squared plus, and instead of writing b, I can write 18 minus a, and square that entire bracket. So I'm replacing b with an entire bracket that's equal to that same thing. And now, suddenly, as I had before, I have this s on the left side, which is sort of like a y variable. And now I just have one single variable a on the other side, which is sort of like an x variable now. But what I have on the left clearly is not in any kind of form that I can work with. So first we need to fully expand it out into standard form, and then from its standard form, we can complete the square. So the completing the square part I'm going to leave to you to do, but let's just talk about how we would expand this out and simplify it. So I have a squared here, and then I start to expand out. So this would give me, actually I don't need a bracket anymore, 324 when I do 18 squared. And then I would also have minus 36a and plus a squared. After a little bit of simplifying there, then I rearrange some terms, and I have 2a squareds and minus 36a plus 324. So that now is a quadratic relation in its standard form using the variables a and s. This is where I'm going to leave it to you now to pause the video, try and put this into its vertex form, and then restart the video to see how mine went. So here's how mine worked out, and I'll just make it clear for you. This is my final vertex form of all of that. And now we can state its vertex. It occurs at positive 9 and positive 162, and then we step back and remind ourselves, what are these values actually representing? Well, instead of x, remember, our first coordinate is a. And instead of y, our second coordinate is the sum of squares value. So that's really an s. So let's step back and remind ourselves, what were we actually asked to find? Well, the question said to find the two positive quantities. We were trying to find a and b. It actually didn't say we had to find the s. We happened to find what that sum of squares is. So it turns out that the smallest you can ever make that sum of squares is 162. But really we are more concerned about what are the two values. What are a and b? Well, we found one of them. We found that the a is going to be 9. But we don't have the other one. So how do we find it? Well, we actually go back to a relationship that we defined that said that b is just equal to whatever you get when you take 18 and subtract the a value from it. So we do this extra little step that says, since a is equal to 9, therefore b is equal to 18 minus 9, if we substitute that in, or in other words, b is equal to 9 also. So it didn't say that a and b actually had to be two different positive quantities, so it's totally okay that it turns out a and b are actually the same. So they obviously both add to 18, and it turns out if you take each of them and square them and add them, that is the smallest combination of numbers that add to 18 that will do that. So we summarize the whole thing and say, therefore, the two positive quantities, the two positive quantities are 9 and 9. In other words, they're both 9s. Let's try one last situation where these max and min values are going to be very important. In this case, it's going to be another maximum value question. So here, again, this is something you might remember from grade 10 last year. So this is a common situation that follows a quadratic relationship. It's sort of like a market research situation here. So a magazine producer knows that normally they can sell 600 of her magazines for $6 each. So normally she's selling 600 of them, and she sells them for $6 each. But often companies tend to do some market research. So they go and they do surveys, and they're asking people, okay, if we changed our price by a little bit, how many of you would still buy our product? And so she starts asking people, what would happen if I raised my prices by 50 cents? And what she notices is that each time she asks people an extra 50 cents, she seems to be getting about 30 less people in sales. So in other words, every time she increases the price by 50 cents, she notices 30 less people are willing to buy her product. So there must be some balancing point, because it'd be great to make your product cost more money, because if it costs $6.50 or $7 or $8, then you're going to be bringing in more money per magazine. But there's a trade-off there, because the more expensive the product is, the fewer people are going to buy it, and that's what she's seeing here with this relationship. So we're trying to find what's the nice, perfect in-between point that will create the greatest possible revenue. In other words, it'll create the greatest amount of money being brought in. So, first of all, let's define some variables here. So we are trying to maximize the revenue. So I'm going to use the variable R for that, which will be measured in dollars. Now, these questions, you might remember them from last year, and if you don't, it's going to seem a little weird what I'm about to do here, but if you just trust that it will lead us in the right direction, I'll show you why it's going to lead us in the right direction in just a moment. We're going to define, as we often do, a variable x, but we're going to let it represent the number of times that she increases the price. But I'm actually just going to put number of price changes. Because what's nice is this exact same process could be used if someone was investigating what happens when they decrease the price. It just so happens that she's investigating what happens when she increases it, but I'm just going to say price changes. So now let's think about what that word revenue means in more detail. So I sort of vaguely defined it, and I said that it's the amount of money being brought in. But it's a very specific word, because when we talk about profit, for example, the profit a company makes means the money that they bring in from all their sales, but we'd also have to subtract how much it costs the business to create their products. When we talk about just the revenue, though, it means forget about how much it costs her to make the magazines. We just care about how much money is she bringing in. So that's really as simple as just doing the cost per each item. So the cost for each item, in other words, for her typical example, it would be about $6. And then we multiply that by the number of items sold. So that is not a hashtag symbol. I'm using that pound sign there to mean number of. So number of items sold. So again, in a normal year for this magazine producer, she would have a cost of $6 each, and then would multiply by the 600 magazines that she's sold. That would be her normal revenue calculation. But now we're trying to do a revenue calculation of a price that could potentially be changing. So it needs to involve this new price change factor, X. So let's think about a different way to write this. Well, R for revenue, we want some way to represent the cost per item. So cost per item, how is that going to be defined? Well, the cost per item originally was $6. So it's normally equal to $6, but it's going to go up by 50 cents every time she changes the price. So in other words, if I change the price once, I add $0.5. If I change the price twice, I add $1. If I change the price 3 times, I add 3 times 50 cents. So in other words, every time I change the price, I'm adding an extra 50 cents. So this $0.5 gets multiplied by X, by the number of times that I increase my price. So again, think about that just logically. If I increase my price once, I'm adding 50 cents. If X is 2 for 2 price changes, I'm adding $1. If X is 3 for 3 price changes, I'm adding $1.50, and so on. let's try and do a similar technique to come up with number of items sold. Because again, normally number of items sold would be 600. But in our case now, it's going to be 600, but it's going down by 30 every time X goes up by 1, every time we change the price once. So we go down by 30 people for every X that increases by 1. So that's a way that we can write that. So all of a sudden, we have this quadratic relationship, and we know it's quadratic because we see that there's an X in this bracket and an X in this bracket. So when we expand all of this out, we'll have a quadratic relation that on the left side is just has our variable R that we're trying to find a maximum value of. And on the right side, we'll have this quadratic expression involving X. So from there, we just need to expand this whole thing out. So R is equal to, now this would be 3600 plus 300x minus 180x minus 15x squared. Then we combine some terms and rearrange, and we have standard form. So negative 15x squared plus 120x plus 3600. Once again, I want you to pause the video at this stage. I'm not even going to show all of the steps for this. I'm just going to pause it at this stage and then restart it in just a moment so that you can see what my final vertex form is. If you want more clarity on that, you can always go and check the completed version of the note for all of the additional steps. But then when I restart it in just a moment, we'll talk about what our vertex form is really telling us and how we can answer the question that way. Okay, so here, as I've highlighted in green, is what I eventually got when I finished completing the square. And if you didn't get that and you're curious as to where you might have gone wrong, go back and check the completed version of this lesson. But now that we have this vertex form, we have to do a little bit of work to really fully answer the question using this vertex form. So as usual, first, let's identify the vertex. It occurs at 4 and 3840, 3,840. And then we have to remember what these things were really representing. So the 4 was like our X, and we'll talk about what X was and remind ourselves in just a second. But then if we actually want to know what the maximum possible revenue is, well, that's what that second value in our vertex is. So the maximum amount of money that she's going to bring in is $3,840, $3,840. But the question was more concerned with what is the price that she should set. Now, X that we found, this 4, is not the price that we're changing it to. X is the number of price changes. That's what we defined it as. So in other words, what this 4 is telling us is that she needs to change the price 4 times. Or in other words, there are going to be 4 price increases, and we should remind ourselves of 50 cents each. So she's going up 4 times by 50 cents each. So if we want to find the price, we actually need to do a separate little calculation. So it's really just, actually, I'm just using this relationship when I find my price. So price is now equal to $6 plus 50 cents, or half a dollar, for each price change. So in other words, that's $6 plus an extra $2, which means it's gone up to $8. So therefore, the price to yield the maximum revenue would be $8.